Hi, so this is the second part of my video tutorial about number theory. So if you haven't watched the first part, you might want to consider watching it now or also afterwards or whenever you want. So this video will be about modular arithmetic. So why do we care about modular arithmetic? So our motivation is pretty much cryptography. So yeah, at least cryptography is one of the applications of modular arithmetic because, well, pretty much most of cryptographic systems nowadays rely on modular arithmetic. So I'll discuss one example in this video tutorial. But let's first make some definitions. So Z modulo n Z. So this is actually a quotient group. So, well, it's not essential to understand what a quotient group is for the purpose of this video. Maybe I'm gonna make another video tutorial about group theory where I will explain it. So, but basically in this case, it's just the set 0 plus nz, 1 plus nz, etc. up to n minus 1 plus nz. So what are these a plus nz's? So yeah, basically nz is just the multiples of n in the integers. And a plus nz is, well, it's just a set of multiples of n plus a. So it would be something like a minus n, a plus n, etc. So if a is equal to b in z modulo nz, then we just write a is congruent to b modulo n. So, for example, I forgot to mention. So in the future, I will not write a plus nz, but we'll just write a. So this a and this b, they actually mean a plus nz and b plus nz. So, for example, 3 plus 4z, this is just something like minus 1, 3, and, well, 7, and so on. And notice that 7 plus 4z it's pretty much the same, so it's also minus 1, 3, and 7, and so on. So that means that we can write 3 is congruent to 7 modulo 4. So an equivalent definition would be that n divides the difference of a minus b. So there's another structure that we care about. So, well, I should mention that this structure z modulo nz has similar properties as z. So we can also define two operations, so addition and multiplication. So I'm not going to write this down formally here because it's pretty clear what it means. It's defined exactly how you would expect it to be defined. So I want to define another structure, namely z modulo nz star. So this is pretty much a multiplicative subgroup of z modulo nz. And, well, so it's basically the elements of z modulo nz such that there exists an inverse element in z modulo nz. So, for example, let's consider n is equal to 5, and the inverse of 1 in z modulo phi of z is just equal to 1, or congruent to 1, and the inverse of 2 would be equal to 3, because 2 times 3 is really just 1 in z modulo phi of z. And so the inverse of 3 is also just 2, and the inverse of 4 is 4. And yeah, notice that 0 does not have an inverse, because if we multiply 0 with something else, it will just be 0. So it can't possibly ever be 1. And yeah, what we want is that the number and its inverse are 1. So that's what we mean with A inverse. So that means that z modulo n z star is actually 1, 2, 3, and 4, because those are the elements of z modulo 5z that have an inverse. So I want to introduce some abbreviations here. So we just write zn for z modulo nz, and we write un for z modulo nz star. So yeah, and now I'd like to write down a lemma. So this lemma says that un is just equal to the element of zn, such that the GCD of a and n is equal to 1. So you can think about why that is true, but basically this follows from Bezout's lemma, or Bezout's identity. Because, well, I mean, if we have GCD of a and n is equal to 1, then we can just write ax plus ny is equal to 1, and that implies that ax is congruent to 1 modulo n. But that means that x is the inverse of a, so we found an inverse, and a must be an element of un by definition. So now you can think about the other direction, and yeah, so I'll just move on. And so notice that according to this lemma, z modulo, or well, let's use our abbreviation. So up is just equal to 1, 2, 3, up to p minus 1. Because, well, every integer that is less than p is automatically coprime to p if p is a prime. So yeah, so recall that this capital P with so this is just a set of primes in the integers. So I want to make another definition. So phi of n, or also the Euler totient function, is equal to the cardinality of un. So for example, phi of 6 is just equal to 2, because, well, 1 and 5 are really the only residue classes of 6 that are coprime to 6, because, well, u6 is just equal to 1 and 5. So also, according to our previous lemma, phi of p will be equal to p minus 1 if p is a prime number. So let's write down another definition. So let G be an element of un. Then the order of G is going to be the smallest natural number, so that G to the power of n is equal to 1, or congruent to 1. I should maybe write congruent to 1. So, and this congruent obviously refers to, it refers to n. So maybe I shouldn't write k here because we've already, maybe I shouldn't write n here because we've already used n. So let's use k here and k here. So let's make an example. So let n be equal to 5 and let g be equal to 2. Then 2 to the power of 1 is congruent to 2 modulo 5. 2 to the power of 2 is congruent to 4 modulo 5. 2 to the power of 3 is congruent to 3 modulo 5. And 2 to the power of 4 is congruent to 1 modulo 5. Thus, the order of 2 is 4. So now let's make another definition. So these elements like 2 in Z modulo 5, they have a special property, namely that the order is just phi of n. And so they have a special name, and we call G in UN a primitive root. If the order of G is equal to phi of n. So, for example, 2 would be a primitive root of 5. So let's write down another lemma, or, well, let's call it a theorem because it's a quite important statement. So, yeah, so this theorem is called Euler's theorem, I think. And it says that if U is an element of UN, then U to the power of phi n is congruent to 1 modulo n. So notice that for primitive roots, this works always because, well, the order of U is equal to phi of n if U is a primitive root. But Euler says that this doesn't only work for primitive roots, but it works for all elements of UN. So let's prove this, or you can also give it a go yourself. So you can pause the video now if you like and try to prove it. So there are many proofs, and well, so I'm gonna show you one proof here. So let U be an element of UN, and well, then UN is equal to, so there are phi of n elements in UN per definition. So let's call these elements U1, U2, up to U phi of n. And well, the thing we need to realize is that this is just the same as U times U1, U times U2, so, and U times U phi of n. So why is that? It's because the function that takes the elements ui from un to u times ui. So this is basically a bijection from un to un. So these elements are pretty much the same. So for example, so let n be equal to 5 and u be equal to 2. And then the first set would be 1, 2, 3, and 4. And the second set would be 2, 4, and 2 times 3, which is 6, which is 1. And 4 times 2, which is 8, which is 3. So notice that these sets are the same. And well, so these sets are the same because this function that just multiplies with u is a bijection because u is an element of un, and thus it has an inverse. But especially, that means that the product of these terms, where I ranges from 1 up to phi of n, is just the same as the product of these u times ur, where I ranges from 1 to phi of n. So the right-hand side is just equal to ui, where I ranges from 1 up to phi of n, times u to the power of phi of n, because, well, we multiply u with phi of n. Well, what I meant is, so we multiply u phi of 1 times with itself, so we get u to the power of phi of n. But, well, it should be pretty clear that the product of these ui's will be an element of un as well. So that means it has an inverse, and we can just multiply with the inverse. And if we multiply the left-hand side with its inverse, then we'll just get 1. And if we multiply the right-hand side with its inverse, then we'll just get u to the power of phi of n, because, well, the inverse and this just cancel. So that's basically what we wanted to prove. So we're done here. So there's another observation. So yeah, let's call this a corollary. So we can observe that the order of A always divides phi of n. And this is, well, I mean, you should be able to prove this now. So I'm going to explain the idea why that is. So if we assume that phi of n is congruent to, let's say, k modulo order of A, then we basically get a to the power of phi of n is congruent to a to the power of k plus j times order of A, where j is just some, so this should be j to the, j times order of A, where j is just some integer. But we can split this up and we get a to the power of k times a to the power of j times order of A, and this is just a to the power of k times a to the power of the order of A times to the power of j. So it should be clear that that is a to the power of k times a to the power, so, well, this is just 1 to the power of j. And so, well, without loss of generality, let's assume that we have chosen this case such that k is less than the order of A. So if k is less than the order of A, that means that k must be 1, because we know that a to the power of phi of n is equal to 1, because that's what we've just proven. Well, that's basically this this Euler's theorem. So yeah, basically this is just equal to 1, so this is congruent to a to the power of k. So yeah, and that means that k must be equal to 0. So this implies that phi of n is congruent to 0 modulo order of A. So order of A will divide phi of n. So we're basically done here. So, I mean, let's write this observation we've just made down. So we always have, so this follows pretty much, well, basically, k to the power of phi times n times some integer. So what do we want to call this integer? Let's call it and, well, we want g to be in un, and, well, this is just equal to g to the k, because, well, we can split this up as we've done in the previous proof, and then we get that g to the power of phi of n times m is equal to 1, and g to the power of k remains. So the observation here is that we can consider the exponent modulo phi of n. Yeah, because it doesn't matter if we add or subtract phi of n. So now I'd like to talk about Diffie-Hellman. So Diffie-Hellman is a cryptographic protocol. And what can we do with Diffie-Hellman? We can, so it usually works for two people. So yeah, and through Diffie-Hellman, they can exchange a key with which they can afterwards, well, communicate secretly. So how does it work? So A and B, so the first step is that A and B agree upon a prime P and a primitive root G. So maybe I should add that every prime number has indeed a primitive root. So I forgot to mention it previously. So that means that we can indeed choose any prime number P and we'll always find a primitive root. So you can try to think about why there is always a primitive root. And well, these numbers P and G can also be public. And well, so A and B may communicate through insecure communication channels if they agree upon P and G. So after A and B have agreed upon P and G, or let's say Alice and Bob, so the second step would be for Alice to choose an element A in Z modulo phi of n Z. So why is this Z modulo phi of n Z? So this relies on the observation we've just made, because A will be an exponent. So yeah, we can consider the exponent modulo phi of n. We've already observed this, so that's why A will be an element of Z modulo phi of n Z. Similarly, Bob chooses an element B in Z modulo phi of n Z. Sorry, this should be here. So afterwards, Alice computes G to the power of A, and let's call this A, modulo P. Oh, and yeah, I think yeah, so this should be P actually. So notice that this is just Z modulo P minus 1. So yeah, actually this is just Z P minus 1. So similarly, Bob computes B modulo P. So it turns out that we can compute these G to the power of A and G to the power of B pretty easily. There are very efficient algorithms to do that, and well, maybe I'm going to talk about it in another video, but I'm not going to talk about it now. So, well, afterwards, Alice sends A to Bob, and similarly, Bob sends B to Alice. And now Alice and Bob can compute B to the power of A and A to the power of B. And now they have a common secret. And why is that? That is because a to the power of b is just equal to g to the power of a to the power of b, and this is just equal to, so yeah, maybe I should write congruent. So this is just congruent to g to the power of a times b, and this is just congruent to g to the power of b to the power of a, and this is congruent to g to the power of, so this is basically just equal to b to the power of a, or congruent to b to the power of a. So yeah, now they share a common secret. And why is it a secret? So basically, we don't know. Idea, so why is this secure? So why does no one else know of this common secret, even though P and G are public? So the short answer is we don't know. And well, that's because, well, no one has managed to find an efficient algorithm to, well, to compute these numbers if you haven't got these numbers a and b, which are obviously private. So, well, the idea is basically, so let g be a primitive root and p be a prime. Sorry, this is and p be a prime, and g is a primitive root of this prime. And now we have a in up, and now we want to compute the discrete logarithm of a. And so, in other words, we want to find a such that g to the power of a is equal to a. So you can try a few examples, and well, it turns out that this isn't easy, and well, yeah. So the conjecture is this is hard. And with hard, I mean that there's no efficient algorithm to do this for very large numbers, and we usually use very hard numbers. Very large numbers. So let's make an example for this Diffie-Hellman protocol. So let p be equal to 97 and let g be equal to 5. So g is indeed a primitive root. You can think about why 5 is a primitive root, and well, I mean, I'm not gonna do this here, but well, I mean, yeah, so afterwards, Alice chooses a is equal to 12, and Bob chooses b is equal to 51. And now they compute their a's and b's. So capital A turns out to be 64, modulo 17, modulo 97, and capital B turns out to be 69, modulo 97. And well, so the last step for them would be to compute their common secret. So that would be a to the power of b, or alternatively, b to the power of a. And well, that is going to be 50 modulo 97. So now you can try to find a to the power of b and b to the power of a, or alternatively g to the power of ab. If you've only got p is equal to 97, g is equal to 5, and these numbers a and b. And it turns out, I mean, that's our conjecture, that we can't compute a to the power of this number 50 easily without knowing these small a's and b's. So you can try to find 50 without knowing small a and small b, and it's probably not going to take very long because, well, that's still a quite small number, but it should give you an idea. Well, that it's going to be pretty hard to compute this common secret if you have very large numbers. So now I'd like to talk about another topic. So quadratic residues. So a quadratic residue is basically what you would expect it to be. It's just a square number modulo a prime p. So a quadratic residue is an element A in UP if there exists an element X in UP such that A is equal to X squared. Or I should maybe rather say A is congruent to X squared modulo P. And notice that according to this definition, 0 is no quadratic residue. So let's introduce some notation. So we write A over B, and this is not a fraction. This is called a Legendre symbol. So this is equal to 1 if A is a quadratic residue. So let's abbreviate this with QR, and minus 1 if A is a non-quadratic residue. So a non-quadratic residue is basically an element of UP, and, well, maybe I should add that P must be a prime, and yeah, so a non-quadratic residue is an element of UP if there exists no such number x such that A is equal to X squared or A is congruent to X squared. So A over P is equal to 0 if A is not an element of UP at all. And, well, so this Legendre symbol is defined for U in ZP, but, well, so, I mean, A can also be congruent to 0 modulo P. So if A is congruent to 0 modulo P, so in other words, if A is a multiple of P, then, well, then A over P is just equal to 0. So if A is congruent to 0 modulo P. So let's write down another lemma. Or, well, let's first make some example. So, for example, if we have n is equal to 5, then the quadratic residues of 5 are just 1 and 4, because 1 is equal to 1 squared and 4 is equal to 2 squared. And the non-quadratic residues are 2 and 3. So we would write 1 over 5 is equal to 4 over 5 is equal to 1, and we would also write 2 over 5 is equal to 3 over 5 is equal to minus 1, and 0 over 5 would be equal to 0. So now let's write down a lemma. So this lemma says if P is a prime, then the quadratic residues are just G squared, G to the power of 4, G to the power of 6, and so on up to G to the power of phi of n, or G to the power of 0. So, and the non-quadratic residues are G to the power of 1 and G to the power of 3 and up to G to the power of phi of n minus 1. So yeah, I should maybe add what G is. So G should be a primitive root, and yeah, if G is a primitive root, then so if G is any primitive root, then this first set is the quadratic residues, and the second set is the quadratic non-residues, or so well, so I mean, you can think about why that is a bit, well, it's really not that hard. It's pretty easy to see that. I mean, it's actually pretty trivial. So certainly these G to the power of I, where I is an even number, they are certainly going to be quadratic residues, because, for example, G to the power of 4 is just equal to G squared to the power of 2. And so you can think about why these G to the power of I, where I is an odd exponent, are not quadratic residues or quadratic non-residues. So so the Legendre symbol fulfills certain conditions. So properties of the Legendre symbol. So, for example, minus 1 over p is just equal to 1 if p is congruent to 1 modulo 4, and minus 1 if p is congruent to 3 modulo 4. And also the Legendre symbol is multiplicative. So it's pretty easy to see that if you consider this lemma, and a squared times b over p. So if this number in the numerator contains a square, then we can just remove this square. So it should be pretty clear why that is. And well, and if we have 2 primes, then we can swap this, and it will change signs exactly if. So it would be, so it would remain p over q if p is congruent to 1, or q is congruent to 1 modulo 4, and okay, sorry. So, well, I actually mean q over p, because that's why we have this property, in order to swap the denominator and numerator. And well, I mean, it's not really a denominator and numerator, but I'm gonna call it that way because because I don't think there exists a name for the denominator and the numerator in a Legendre symbol, so I'm just going to call it numerator and denominator, even though it's not really a numerator and denominator, because it's not really a fraction. So and if p and q are both congruent to 3 modulo 4, then it's just going to be q minus q over p, so the sign will change. So we also have a property which allows us to compute 2 over p pretty easily. So 2 over p is going to be 1 if p is congruent to plus minus 1 modulo 8. And it's going to be minus 1 if p is congruent to plus minus 3 modulo 8. And maybe I should add, if we say a prime number, so for example here p and q are primes, and this p should always be a prime, but really we don't mean a prime, because we don't want it to be 2, so it should really be an odd prime. So I should add that. Let p and q be odd primes. Okay, so let's compute an example. So I want to know if 31 is a quadratic residue modulo 1009. So notice that we can swap the sign, swap the numerator and denominator, so we get 1009 over 31, because 1009 is congruent to 1 modulo 4, and this is just 17 over 31. because 1009 is congruent to 17 modulo 31. And we can swap the numerator and the denominator again, so we get 31 over 17, because 17 is congruent to 1 modulo 4, and now we get 14 over 17, and this is just 2 over 17 times 7 over 17, because of the multiplicativity of the Legendre symbol. So 2 over 17 is going to be 1, and 7 over 17, so 2 over 17 is 1, because 17 is congruent to 1 modulo 8. And 7 over 17 is just going to be 17 over 7, because 17 is congruent to 1 modulo 4. And that is going to be 3 over 7. And that is going to be minus 7 over 3, because 7 and 3 are both congruent to 3 modulo 4. So yeah, that's because of this property here. 7 over 3 is just 1 over 3, but we know that 1 is always a quadratic residue for all primes, because 1 is just 1 squared. So that is equal to minus 1. So that means that 31 is indeed not a quadratic residue, modulo 1009. So there's an interesting problem with quadratic residues that I've found, but I think I'm going to make another video about it, because, well, we're pretty much out of time. So yeah, I guess this is the end of the video. So bye, see you soon.